Hello everybody, today I'm going to discuss the third problem of the 2024 US Open contest, problem Farmer John's favorite permutation. In my opinion, this has been the hardest problem from all of them in the problem set, although also the first one has been quite difficult, but not in the same way as this problem is difficult. So let's get started. In this problem we are given a permutation of length n, and we also want to reconstruct the original permutation based on another array that we are given by the other farmer, and we know the rule in which we need to reconstruct the original permutation from the array we are given. So we know the construction from which we arrive to the second permutation, and we want to arrive to the first permutation. So in a way we want to kind of do some sort of reverse engineering to get this done, and we need to be careful at how to do it because n is up to 10 to the 5 and we will have to find a bunch of observations to get this done. So we know that for the fourth example from 211, we know that here we can obtain 3124 as the lowest lexicographical permutation, because by simulating the process we can just obtain 2 as we remove the 4, then 1 as we remove the 3, and then 1 again as we remove the 2. So this is how we obtain the permutation, and also we know that 4, 2, 1, 3 will produce the same result. So now the very first observation you can find right away from this sample is that for a given permutation, if we know the result it's gonna produce, also the reversed permutation will do the same thing. So 3, 1, 2, 4 and 4, 2, 1, 3, because one of them is the reverse of the other, will always produce the same thing, because the process doesn't really care about whichever value is the first or the last, and these permutations are actually the same thing from the context of the problem. So this will be quite helpful, as you will see a bit later. Now, how do we come up with observations and ways to think at the problem? So first, at least something you can do if you don't really know where to start is to start by writing some brute force. And what better brute force to write than just generating all of the permutations and seeing what happens when you apply the process. And after I tested it out for, let's say, values up to around 10, I just did here like all of the permutations using the n factorial algorithm and just did the process. I observed that for all of the permutations, the array we are going to obtain has at least n minus 2 distinct values. And this is going to turn out to be a very important observation. Also, if we go further down the line, if the array has n minus 1 values, then it means that we can place the last one at one of the ends, and also this means that something like 1 will always be at one of the ends, because it will keep popping the values from the other side of the array. So what we can do in that case, when we have n minus 1 distinct values, so every value is distinct in the array H, is to put the remaining value at the end and then just write the array in the order we are given, or in the reversed order if that turns out to be better. So we dealt with the case when we have n minus 1 distinct values. Now what do we do if we have n minus 2 distinct values? Actually, this is going to turn out to be quite interesting, because all we have to do now is that we know where the two values that are missing, we know where the two values are, the values that are missing. So they will be at one of the ends, because if they were not at one of the ends, then by applying at least once the operations, they would have been somewhere in the array, so not at the end. So we can start the array just like I showed here with something like, so in this permutation, so 1, 5, 3, 2, 7, 8, 1, I mean it's not a permutation, but like 1, 5, so sorry, I had a bunch of stuff from the previous problem, so 1, 5, 3, 2, 7, 8, 1. Here the values that are missing are 4 and 6. And of course it's more optimal to put 4 in front because it's smaller than 6. And we know the order in which we achieve these values. So we can say that so if P1 is greater than Pn, we write down P2 and we remove P1 from the permutation. So as you will see here, we can just place 1 to the right of 6 and then remove 6 from the permutation if we were to have simulated the process. Now 5, we have to place it next to the value that's greater. So we will place it like here and we remove 4. 3 will be placed to the right of 5 in the same way. 2 will again be placed to the right of 3. 7 will be placed to the right of 1. And then we will do the same with 8 here. So the final permutation is going to be 4, 5, 3, 2, 7, 8, 1, 6. So something very important we just found from here, and it can be easily proved, is that if we know the values that are missing, the rest of the permutation will be let's say uniquely determined. We know where to place each value based on these informations. So now all we have to do based from these conditions is to check out if the array we are given has at least n minus 2 distinct values, and if it has, then in this case we are going to be able to reconstruct the permutation, simulating the process from the statement. But at the same time we need to be careful that the permutation is actually valid and respects the construction that we are given. So as you can see in the implementation, I just check with a set if everything exists. I could have also done it with a frequency array, so there is no need of a set. And then I also checked if there are n minus 1 permutations that show up. The remaining value has to be different than 1, because if it's 1 then it doesn't make any sense. And then if not, I just print negative 1. If there are less than n minus 2 values, then again I print negative 1. And now I just want to find the values that are missing. So I start by filling the first and the last value. And then I simulate the process according to the statement, just like I showed you earlier. So I just do that, and now when I check the solution, I also want to reconstruct the answer to make sure that it actually matches what we want to do. And if that happens, then we are good, otherwise not. And then I just print out the permutation as it shows. So as you can see, this problem is also quite a bit implementation heavy, but it's mostly just dealing with cases, just like in the first problem maybe. And from there you should be able to have, let's say, a smooth implementation, as you will see. So as a conclusion, to wrap up the solution to this problem, we need to be careful at finding observations. Brute force can be a very good friend of yours for these problems. And the two main observations are that first, the number of distinct values in H should be at least n minus 2 or n minus 1. And if this thing doesn't happen, then we are going to just say negative 1. And if this thing works, then all we need to do is to simulate the process and see if it works. So we will need to be careful about that. And last but not least, we need to check if all conditions work and be careful about implementation. So if you enjoyed watching this video, please like, share and subscribe to the channel. It helps me a lot, especially these days where there is a lot of competition out there, and I want to provide the best videos so that everyone can watch them. And also, if you want more ways to interact with me, check out the website, the link is in the description, and you can see more ways to interact with me, including classes, courses, and many other ways. So thanks for joining the video and watching it, and I hope you found something useful from having watched the 3 USACO problems. The links are in the description. And stay tuned, as I will upload more educational output, more videos and other similar things. So thank you and cheers.